Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in lecture 14. Okay, student, this is lecture number 14, not 13. In lecture number 13, student, basically you people see that we discuss the unbalanced movement. Okay, what is unbalanced movement and what are the different cases in which unbalanced movement basically generates in a slab or beam column joints. So although in equivalent frame method, as we did in from lecture number 1 to lecture number 10, we see an unbalanced moment is calculated in moment distribution table. But in the case of the flat slab system, you see how we do that calculation or how we calculate unbalanced moment. So we thoroughly explained this in lecture number 13. So go there and watch that lecture, because if you don't understand lecture unbalanced moment, then it will be difficult for you to understand lecture number 14. So to start lecture number 14, sorry, I would recommend you to please recall your the basic concepts regarding the unsymmetrical bending. Okay, it is very important. You see, this is kind of a case study. Okay, that here we have a load or observer and here we have a column. So here you see that the person stand right here and here is the column. So the person causes movement about the z-axis as well as about the y-axis. Okay, it causes movement about the y-axis. Remember, this notation means movement about the y-axis. This notation means movement about the z-axis. But remember, this is also important that this person is also, remember, this person also exerting a vertical force over this column cross section, and that also causes the compression of that column. Okay, similarly these movements also causes the shear. Okay, you have to understand the bending formula M by I equals to stress over C. So this stresses are the compression and tension or the flexure stresses within this column will be MC divided by I. So the combined stress distribution over this column will be, because we have a load, so there will be direct compression due to the person load, and that will also be P by A. So the combined stresses will be P by A plus minus that moment MC divided by I. These will be the net resultant forces. Remember, this is very, very important to understand that this is the direct stresses, compression stresses, which is caused by the load of the person, and here you see the complex thing, because here you see movement due to Y, movement due to Z, and it's the different corners of the beam section, because this is corner, this corner, this corner, and this corner. Some forces are tensile, some forces are in compression. And let me share you one example. You see this load which is acting, so it will causes the movement about z-axis. Similarly, you see here this horizontal force. So this horizontal force will causes movement about the x-axis. Okay, and that vertical forces causes movement about the z-axis. So about the z, the stress distribution will be looks like in this shape, and you see here. Now you see that this movement which is about the y-axis causes that portion of the beam in compression while this portion in tension. But here you see, due to mz, this portion will be in compression and this portion will be in tension. Now the net result at this corner, you see this is in tension and this is in compression. So tension, compression, okay, upset each other, and we got 0 if the magnitude are same. So you see here the stresses at this point is 0. Now let's say at this corner, so you see here compression, and similarly at this corner you see here compression. Okay, you see here compression. So adding these two compressions will give birth to the larger compression stresses. Okay, so you must know about the concept of unsymmetrical bending, because if you don't understand these things, the today lecture will be so difficult for you people. So let's start the lecture. Okay, now we have slab column connection loading with shear and moment. We must understand some technical terms relating with the moment transfer. Okay, first of all, the critical parameter you see right here in the case of interior column. Okay, how we can calculate the B naught. Okay, you already know this, and we already explained this in lecture number 11. Similarly, in the case of the H column, how we calculate B naught, and similarly in the case of the corner column, how we basically calculate the B naught. Okay, now you must know about these criterias A and B. I already explained this in lecture number 11, so go there and watch what does these criteria means when basically you have to count R, S and WV. This is very important, and I explained this in lecture number 11, right? Now the next thing is very important to understand what is the centroidal axis of shear parameter and centroid of the column B1. What is B1, B2, C1, C2 and CAB and CCD. Okay, this is very important. You see, this is an H column. In H column you see this axis, which is Z axis, and similarly this axis, right? This axis, this one, which is passes from the centroid of the column, but this Z axis is not passing from the centroid of the column. This is very important. Okay, this point is called the centroid of the shear parameter, not the centroid of the column. The centroid of the column is this one. This dot line represents the shear parameter, which basically present at a distance of d/2 from all the three faces of the column. Okay, d/2 to this side, d/2 to this side, and d/2 to this side. Now this is important, this Z axis, and sometime it is denoted by W, or sometime it is denoted by Z1 and Z2. Okay, so these axes are basically called the centroidal axis of the shear parameter, right? Now what is AB face? This is the face, or you can say the front. For example, this is the edge of the beam, edge of the slab, sorry. This is the edge of the slab, so this is the face of the shear parameter. Okay, and this AC and BD is now the sides, and this is the back side. Clear? But remember, this kind of, this is, say, let's say this is front side, this is back side, and now these are the sides, right? These are the sides. BD is the side, AC is the side. But this kind of notation works when we considering the moment about the Z-axis. If we are considering the moment about the W-axis, then remember, then the things will be reversed, and in this direction. Remember, the movement is in this direction, which is the counterclockwise direction. So in that case, this BD will be your front, AC will be your back, and AB and CD will be your sides, right? This is very important, because when we are analyzing the the system or the slab system in east-west direction. This is our east-west direction, let's say. So this AB face will be our front and this CD will be our back, right? And here we are basically considering the movement about the z-axis, right? So the movement is now hitting this. Look to this arrow. The movement is hitting AB side, so that's why this is front. If the movement is reversed, let's say the movement is acting in this direction. Movement is, although it is about the z-axis, but it is now in clockwise direction. Then remember, this is your front and this is your back. Sides will be remain unchanged, because you know the movement is changing. Sometimes the movement about the z-axis will be counterclockwise, sometimes it may be anti-clockwise. This should be remembered. Similarly, from w-axis the movement may be clockwise, anti-clockwise, and movement may be clockwise. And in that when the sign is changed, means the direction of the movement is changed, the distribution of the stress is also changed, right? Now the front width of the shear parameter now is equal to C1 plus D, okay, which is represented by B1. Now what is B1 and B2? This is very important. By understanding the movement transfer, you must know about the B1 and B2. Here I basically write B1 is the total width of the critical section measured perpendicular to the axis about which the movement acts, and B2 is the total width parallel to the x-axis. This is very important, right? You have to understand right now that, let me rub these, because you don't need to be confused with this moment. We come back here. See, here we have yes, we are considering, let's say, the movement about z-axis. Let's say we are considering the movement about z-axis. This is very important. You must understand B1 and B2. Now here you see, let's say the movement is acting about the z-axis in this direction. Now you see, according to this statement, B1 is the total width of the critical section measured perpendicular to the x-axis. Now here you see, if according to this statement, remember, this B2 is now your B1, and this B1 is now your B2. This is very, very important. Okay, B1 is the total width of the critical section. B1 is the total width of the critical section measured perpendicular to the axis about which the movement. So the movement is acting about the z-axis. So B1 is that side which is perpendicular to the z-axis. So this side is parallel to z-axis. So that's why this is B2. And this side is, as you see here, it is perpendicular to the z-axis. So that's why this is your B1. If, let's say, the movement is acting about the w-axis, then this kind of notation will be right. Okay, let's say the movement is acting about the w-axis. In this case, remember, as this is your axis and this side is perpendicular to this axis, so that's why this is now right. This is B1, right? And here you see that this side is parallel to the w-axis, or the axis through which movement is acting. So that's why this is now B2, right? And how to determine B2 and B1 in the case of H? Okay, you see here B1 will be C1 plus D and B2 will be C2 plus 0.5 D, right? Now this is important. In this case, you have to understand CAB and CCD. This is important. Now if we consider this case, the movement in this case, remember, in this case you see there is a symmetry. Okay, there is a symmetry. This axis passes through the half portion of this side and half portion of this side. Okay, because it passes from the centroid of the axis. W axis passes from the centroid of the axis, so that why there is a symmetry. In this case, remember, your whole A, B, C will be changed. This B will become your A, this D will become your B, and this will be C, and this one will be D, right? And now you must understand that in that case, remember, this is your CAB, this one will be your CAB, right? And this one will be your CCD, this one CCD, right? But both will be same because there is an axis of symmetry, right? Let's say the moment is acting about the Z axis. So in that case, as the moment is acting about the Z axis, remember here Z axis close to AB face, and from the AB face the distance to the centroidal axis Z axis is now CAB, right? And to the back side or CD side, it is denoted by CCD, and this distance will be larger than CAB, right? So this axis, Z axis, is close to this axis, so there will be greater amount of stresses along the AB side. It must be remembered. Now similarly, you have to denote C1 and C2. C1 and B1 will be the same side, and C2 and B2 will be on the same side. Okay, this is very important to understand B1, B2, C1, C2 notation in the case of the H column. If we have, let's say, the corner column, so in the corner column you see here Z2 axis and Z1 axis, or this may be represented by W axis, right? Now here is the centroid of the column, right? And here is the centroid. You see here both axes intersecting at this point, so that why this is now the centroid of the shear parameter, and the Z1 and Z2 are the centroidal axis of the shear parameter. This is very, very important. Now G2 and G1 is the distances. G2 is the distance which is basically from the centroid to the Z2 axis, right? And G1 is the distance which is from the centroid to the Z1 axis, right? And here we see that, let's say for example, we assume that movement is acting about the Z1 axis, right? Now in that case, let's say this is not, movement is not acting about the Z1 axis, movement is acting about the Z2 axis. Okay, now in that case AB will be your front and CD will be your back, and AC and BD will be your side. So AB, so the distance from Z2 to AB is denoted by CAB. It should be remembered, in some books you see this may be X2, or this may be represented different book uses different notation, but you must know this AB side. Okay, you need to look to the direction of the movement is acting in this direction, so this one will be your AB, this will be your front. Okay, and if the movement is now, let's say, in the clockwise direction, so then this one will be yours front. So you must know this kind of notation. The next thing is the CAB and CCD, right? And if the movement is acting about here, so in that case the things should be reversed. Okay, although you see here this is, let's say, movement is acting about this one, so this BD will now your front or your face, so you may change the places of A, B, C, D as we did in the H column, or if you doesn't change the places, then you see the notation will be changed here, right? CBD and CAC, right? If you don't want to change the notation A, B, C, D, so in that case, let's say you are using this notation, although this is your front and this is your back, clear? This is your back. So in this case, now the CBD will be this distance, because this is Z1 axis, this is centroidal axis. So BD lies the distance of CBD, and similarly AC is the distance which is the side which lies at the distance of CAC from the Z1 axis. We will determine the CAC CBD distances by using formulas, but at this time you must remember what does it mean. Now similarly you have to understand B1 and B2 as well, right? If let's say we are considering this moment, right, because the corner column we have both moments, moment about Z1, moment about Z2. Now let's say we are going to analyze the structure or the slab system in north east-west direction, okay, in east-west direction. So in that case, remember, this is the moment, so you already know that B1 is the distance, is the side which is perpendicular to the moment axis. So then in that case, basically this side will be your B1 and this side will be your B2, right? But if we consider this moment and the moment about the Z axis, so you must remember that then it will be, this side will be now your B1, this CD will be your B1, and this BD will be your B2, right, as we did here. So this kind of notation must be remembered, where what does B1 mean, what does B2 means, and how it changes. In the case of the interior column, as you see, this dash line is the critical parameter, and this side of the critical parameter is C1, this side of the column plus D, and similarly in this case the side of the critical parameter will be C2 plus D. Now this side is C2, right? But in the interior column, this is assumed that the centroid of the column is coincide with the centroid of the shear parameter. So that why we don't need to look at Z1, Z2, and similarly you see here that this is face C and this is face B, okay, and this is face A and this is face D. Now you see this is CAB, and CAB and CCD will be in this case same, okay, they will remain same. So this is your CCD, okay, this is your CCD, and the axes are CC, okay, the axes are CC. So and this is the critical section. So in the interior column case, we don't need to consider Z1, Z2, we just CAB and CCD which are same, and here we don't need to be confused with those kind of notation. So this kind of notation understanding is very important, because we will use this in the coming section. Now after understanding the notation, the distances, what is Z1, Z2 and B1, B2 means, we come back to the main theme of the lecture, that in the most of the practical cases in the interior column is designed for power axial case, okay, this is okay. But if you have let's say you see here, this is the shear parameter, and you see the shear parameter, and this is the shear stress distribution. So the shear stress distribution is nearly, you see, they are assumed to be uniformly distributed, because at the interior joint there is insignificant movement. If it is wind load or any kind of lateral loading is acting, then there may be some significant amount of movement. If it is an unbraced structure, if it is a braced structure, like let's say you are providing shear walls, okay, left in the interior of the structure, so in that case there will be insignificant movement over the interior joints or interior columns. But if it is an unbraced structure, you don't provide shear walls, okay, so in that case basically there will be some kind of significant amount of movement. So you see this force, and this force is basically acting over this section of the column, and we assume the uniform distribution of the shear stress along the shear parameter. Remember, uniform, and that uniform shear stress will be defined by VU. We already know about VU. What is VU? That is QU times area, tributary area. Okay, we already did this calculation in lecture number 12 and 11. But as I already explained this, that when you have lateral loading, so unbalanced movement, it may act, and if earthquake loads, wind loads, so due to that there is significant amount of movement. This is very important in such situation. If you have lateral loading and you have gravity loading, the joints are the analysis of the joints will become very complicated, because in that case we have flexure, we have shear, we have torsion. A combined loading case is produced, and as I already explained those concepts here, that you have combined loading case and the joints are become more complicated. Now here we see an uniaxial bending case. You see here the force is acting, let's say this is V, U, and you see the movement is now acting about the x-axis. So if there is movement, let's say uniaxial movement, so you see here MUV. We will understand what is UV mean, but at this time let's say we have a moment right here which is acting about the z-axis. This is an H column, right? This is an H column, and I think so you must understand what is z-axis means. This is now x2 and x1. So this is I already explained, different books use different notation. X2 is what? It is CAB, right? And x1 is CCD. Okay, this is my face C, this is a C, D, and this is A, B, right? You must understand these notations because different book uses different notation. So now you see here that this side is perpendicular to this axis, so that's why this is now your B1, right? And this side is parallel to Z axis, or the axis through which movement is acting, so that's why this side is now B2, right? Now, so remember this side is C2, this side of the column is C2, and this side of the column is C1, right? This is C1. Now, as the movement is acting right here and it hitting this place, so this side will be in compression and that side will be in tension. Okay, so those compression and tension forces basically creates shear stresses along the shear parameter. You see, this is the shear parameter, and the 3D view is basically here. We denote the 3D view right here. This is the depth D, right? And this is B0. Now those, because due to this movement, okay, this side will be in compression and that side will be in tension, as we already understand this right here. So those compression and tension causes stresses, shear stresses along the shear parameter. And what will be the amount of those shear stresses? Remember, that as you see here, the flexure distribution of the stresses, okay, it will be looks like in this shape. It will be looks like in this shape. Okay, now here the stresses are maximum and here, and then it will decreases. So that why you see the shear stresses will also be on this shear parameter. As you see here, the shear area of the shear parameter, the slash lines. So you see the shear stresses is also maximum at the corners, and here it will be 0. Okay, so mx2 divided by jc, you already understand this equation which is right here, mc by I. This is shear stress distribution. Okay, we will understand this thoroughly coming section. And this kind of movement also causes the horizontal shear. Okay, and the horizontal shear, right, you see here along the top and bottom of the slab, and it is denoted by VUH. Okay, and it is calculated by M du2 divided by JC. Let me discuss this MUV. Okay, this is very important to understand right now. Here we have, right, that what is MUV and what is MF. Okay, remember, as we already discussed in lecture number 13, unbalanced movement. So that unbalanced movement which is acting over the joint, now at some part it is, as we already know, that at the slab column joint, that unbalanced movement transferred to the column. Now the portion of the unbalanced movement which is transferred to the column by flexure is denoted by MF, or it is also denoted by MUB. It is also denoted by MUF, MUB. Okay, so this is the movement, okay, which is directly transferred to the column from the slab through direct flexure, right? And MUV is that portion of the unbalanced movement, okay, which is transferred by eccentric shear. Remember, which is transferred to the column from the slab by through eccentric shear. And you see this gamma V and gamma F. Gamma F is that percentage portion, okay, of the unbalanced movement which is transferred to the column by flexure, and gamma V is that percentage portion of the unbalanced movement which is transferred by eccentric shear, right? So what is now the gamma V and gamma F? It is from the Hansen et al. Research. It is experimentally found that 60% of the unbalanced movement is transferred by direct, mean that gamma F will be U0.6, right? And gamma V will be, now the rest of the movement will be transferred through eccentric shear, that is 0.4. So if you find gamma F, you just need to subtract. How to find gamma V? So it will be easy, just 1 minus gamma F. Okay, you just need to subtract from 1, you got this gamma V. And gamma F can be determined by using the ACA equation, which is this section 13.5.3.2, and this is the formula for the gamma F. Now what is B1 and B2 I already explained. It should be, remember that there are different cases. Remember, for a slab attached to the side, remember these values may be changed. Okay, different experiments found, in those experiments it is found that these values may be changed, right? You see here, for a slab to attach to the side of a wall, okay, if a slab, let's say, is attached to the side of a wall. Let's say this is the side of the wall. So the slab is attached to the side of a wall. In that case, gamma f will be 1 while gamma v will be 0, right? But if the slab is attached to the end of the wall, okay, let's say it is the slab attached to the end of the wall, so in that case the whole moment is transferred by eccentric shear. In that case, gamma v will be 1, right, and gamma f will be 0, approaches to 0. It is very important. In this case, the whole moment is transferred to the wall by flexure, not by shear. And in that case, the whole moment is transferred to the wall not by direct flexure but by eccentric shear. This is very important to understand. And similarly, from this graph you can determine gamma f and gamma v. You see here, you find the gamma b1 b2 ratio, and you just go off here, and if your b1 is less than b2, you use this curve. If your b1 is greater than b2, so you will use this curve. Okay, so you have to come here, and here is your gamma v and gamma f value. Remember, when your gamma v value is increases, your gamma f value you see here, it decreases. And if gamma f value increases, your gamma v value decreases. So this is the portion of percentage portion, which basically mean that how much percentage of unbalanced moment is transferred through eccentric shear and it is transferred to flexure. Now you must understand this diagram, and from this diagram you must understand the transfer width, but we will understand this in later stage. Okay, let me explain this example. Okay, this example is very important, and this joint is very important to understand. Now you see in this joint that we have VU and MSC. So VU, you already know, this is the shear, okay, which is QU times tributary area. And you see here the situation can be modeled as shown. Here VU represent the total vertical reaction to be transferred to the column. We already understand this. But MSC, which is the slab column moment, represent the unbalanced moment to be transferred both at factored loads. The vertical shear force VU causes shear stresses distribution more or less uniformly around the perimeter of the critical section, as assumed earlier, represented by the inner pair of vertical arrows. This one, we already know this. This is a kind of reaction or loading from the slab to the column, and this one, this is due to from the slab to the column. Now the sum of these two shear give you VU. Okay, and remember here it says that if you have both the vertical force VU causes shear stress distribution more or less uniformly around the section, as I already explained this right here. Okay, a uniformly distribution of the shear stress due to VU. But if, let's say, acting down, if the unbalanced moment MSC causes additional loading on the joint, because you already know we have unbalanced moment, and if unbalanced moment acting, it causes additional loading at the joint, represented by the outer fare. You see here at one side it is acting downward, while on the other side you see here it is acting up. So it may, you understand here, which add to the shear stresses otherwise present on the right side. And on this side you see it adds with this VU in the sketch and subtract on the left side, and it will be subtract on the left side. So due to unbalanced moment, you see that extra loading also, some additional loading also adding to the joint with VU, in addition to the VU. Okay, so this is very important. Now let's see how we basically such kind of loading acting, let's say such kind of loading acting, how we get basically. You see here that VU and MC is acting over the centroid of the column. Okay, but basically due to unbalanced moment, in the case, this is in the case of the interior joint, but in the case of the corner column, in the case of the edge column, it doesn't acting over the centroid of the column. It is very important, and it acts over the z axis, as I already explained. Okay, in this case you see that in the cases of the interior joint, they both VU and unbalanced moment acting over the centroid, which is passes through the column centroid as well. But in the case of the corner column, it acts over this point. Okay, and it acts in the case of the edge column, it acts over this point. So here you have VU and here you have unbalanced moment. We have to transfer that moment to the centroid of the column, and when you transferring that shear, okay, and that movement, right, so it causes some extra movement right here. It causes some extra movement right here, because you see you have to see this VU, right, this VU. So VU times this distance G, so the net movement will be this moment plus VU into G, right? And this is important, and you will understand this by understanding this example. You see here we have a column section 12 by 16 inch, and we have a shear parameter, you see here, which is whose size are 18.75. this is B1, and you see this side is 21.5. now you see this is B2 and this is B1. Now what does it mean? That in this case the moment is basically acting over this axis. This is the Z axis now. So you already know B1 is the vertical side to the centroidal axis of the shear parameter, and B2 is the parallel side. Now this face D2, you already know this shear parameter, and AB notations are the same, because this is now our front side. This is our front and this is our back, right? So this is our AB and this is our CD. Now it is important that you have to find out this CAB distance, CCD distance. Okay, in our example inshallah you will see how we calculate the CAB and CCD. Although this in this example these distances are already given, you have to just understand the transfer of these moments to the centroid of the column. Now you see here this is the centroid of the column. Okay, and if you draw the W axis or Z2 axis, let's say this is W axis as we discussed in the beginning of the lecture. So you see here this is now the centroid of the shear parameter. This is now the centroid of the shear parameter, as we already explained right here, this one. Okay, and this horizontal distance is denoted by G, right? And now you see here we have to transfer those shear and those movement to the centroid of the column. Now you see here that this is the centroid of the shear parameter, and at that shear parameter the shear is given, which is this one, 31.3 kip, and the movement, the unbalanced movement, is 45.6 kip feet. Okay, this is the unbalanced movement which you basically determine from the by moment distribution table, from moment distribution table, or from as we explained in lecture number 13. Now they are it is assumed, basically it is not explained in the ACA code that where this unbalanced movement act. Okay, but it is assumed that it is acting over the shear parameters, over the centroid of the shear parameter. Okay, now you see here this is the centroid of the, this point is the centroid of the column. Now you see this cantilever portion, and we already, this is 4 inch, we already did this example in lecture number 10. Okay, this example we already thoroughly explained in lecture number 10 by using the equivalent frame method. And the loading of this cantilever portion is, you see here, it act over the face of the column, and this is 4 kf. This is already given. Now if we add this, okay, if we want to transfer this shear to this shear parameter centroid, so you just need to add this shear with this shear. You got total shear. Now this is VU, which is, you see here, 35.3. But at this point, which is the centroid of the shear parameter, now this, what will be the net moment if we are considering the effect of this shear? So as you see, about this centroid, it causes a negative movement or an anti-clockwise movement. So, and this is a clockwise movement. So the movement which is caused by this shear will be 4 times this distance, 8.79 inch. Now you just need to multiply this distance with this shear with this distance and subtract it from 45.6. You got 42.7 kip. Now this is now our total or the net unbalanced moment. If you are interested to find this shear at this point, this shear at this point, and this the net moment, or let's say this is VU and this moment, so it can be easily determined. Remember, the total shear will be remain constant. This is also remain VU, but the moment will be changed because this moment about the centroid, it will be 42.7 plus that shear VU times the distance, this is distance G. Okay, so how to determine this G? This G can be determined from because we know this is the half of column, which is 6 inch. So 6 minus this this distance, which is, you already know this distance is CAB, this one CAB. So you just need to subtract that CAB. Okay, CAB, you got this net moment. Okay, so this is how, by using the equation of equilibrium, we finally convert the moment to the centroid of the column, and then we distribute the, remember, for the design of the column, remember, this VU will be replaced with PU. Okay, this will be the total vertical loading at the column, but this MU is distributed to the top column and bottom column in view of its stepnesses, and then for those movements we will design the column. Now I think so you will thoroughly understand this concept. Now you see here, this is an interior column, an interior joint. So you see this movement means that it is acting in this direction or about z-axis and about anti-clockwise. So this is an anti-clockwise movement, is a clockwise. The net movement will be, you will see how we determine the net movement, as we already explained this in lecture number 6, 7, I think so. So remember, we have direct shear, right, at the critical section, and you see the shear stress distribution. I already explained this, uniformly shear distribution. But due to this movement, and this movement is basically, you see here, it is important that the unbalanced movement, and in the unbalanced movement is divided into MUF, yeah, or MUB, okay, and MUV. Okay, so we divide the total unbalanced movement into two parts. The one part which is directly transferred through flexure, the other part which is transferred through this eccentric shear stress. Now this eccentric shear, you see the distribution at this face is uniformly distributed, but here you see the arrows lines that it looks like in this shape. You already discussed it. Okay, now here you see the variation like in this pattern. Okay, now we add these two results. You see here, this, by using this formula we find the uniformly distributed shear, and by using this formula, this is gamma V into mu1 minus mu2. So if you find the net movement, which will be your total unbalanced moment. So if you find the unbalanced moment, you will basically find it from moment distribution table or by using the direct design method approach we discussed in lecture number 13. So you have to multiply gamma v times c. You already know that it is from centroidal distance to the top fiber, and jc, we will explain this c and jc in coming lecture. Now gamma v, we already discussed it. So this is now the shear stress at the face of the shear parameter. So we add these two results. Remember, here is, you see the arrows which is down, here you see the arrows which is down, and similarly here you see the arrows in upward direction, and here you see the arrows in downward direction. So it means that, let's say this is compression, so it will be negative, it will be negative, so negative with negative both adds, so the net shear stress will be maximum at this face, right? And here you have negative, and here you have positive sign, because here you see tension, here you see compression. So that why it will offset each other, and you see you got the lesser amount of shear stress at this phase. Okay, so this will be now our total shear stress. It is important. In figure 1371, this is our total shear stress. Similarly, in the case of the H column, you see here, this is the shear stress distribution at this phase, but here you see the uniform, but here you see here, this is maximum right here, but you see here, this is let's say this is my z-axis. Okay, so at z-axis, the shear stress here, it is 0, right? And similarly, the shear stress distribution is now, this is due to vu, and this is due to the mv. Remember, this is due to mv. This shear distribution due to mv, remember. Let me, so you see here that this is the shear stress distribution due to mv, right? Gamma v times mu. This is mu. Okay, this is mu, because you have to multiply gamma v with mu, right? This is, must be remember, you have to multiply gamma v with mu. Similarly here, okay, this is mu. So gamma v is the percentage portion which is transferred by shear. So you this is the total unbalanced moment. So total unbalanced moment times gamma v, it will give you that amount of the moment which is transferred by the eccentric shear. Similarly here you see, this is mu times gamma v. Now shear stress distribution will be look like, you see here that here it is maximum and here it is minimum. Now you add these two, you got the net shear distribution in this pattern. Okay, and we use, you will see, we will use the basic formula by adding this effect, that is vu. Okay, vu divided by b naught into d. At this case here, in this case, we will use minus sign gamma v times mu divided by c, right? And at this side, we will use the plus sign. Okay, because this is more as compared to this one, so that why at this side it will be a negative sign, and at this side it will be, we will use a positive sign. Okay, so we will use this basic equation by using the total shear stress distribution. This is the formula which I already explained, and sorry for this, this is okay, this is JC, right? This is JC. We will understand JC. There we have C, right? And this is the basic equation which I already explained, and you already know that this is, remember, this is VU, right? This stress is not that stress, that linear stress. Okay, this is basically shear stress. Okay, this is basically shear stress, and we will find that shear stress due to unbalanced movement due to eccentric. VU is factored shear from slab to column, and VU is the shear stress. Okay, this is the total shear, but V small VU is the total shear. It is the shear stress at critical section at d/2. MU is the factored moment which being transferred to the slab. Gamma V is the fraction of the moment that is transferred by shear stresses. Okay, and I already explained gamma V equals to 1 minus gamma F. Gamma F is the fraction of the moment that is transferred by the direct flexure, right? So I already explained these concepts. Now remember, once you got your VU, right, the value which you got right here, this one, VU, so you have to compare this shear stress, which is the total shear stress, against VC. Okay, if this one is more than this value, so the design is okay. There will be no punching shear failure. If it is less than, so you have to design for this moment, for this extra shear. Okay, you have to provide shear reinforcement, or any other arrangement you have to provide it, as we discussed in lecture number 11 to lecture number 13. Now what is pi VC? For beam shear it will be this equation. By using this equation, and for punching shear we will use these three equations. We already explained this in lecture number 13, sorry. We already explained this, right? And next thing, this one, this is very important. See that gamma F and gamma V, this is important. Now you see MUV and MUF. So the moment, okay, which is directly transferred to the column from slab to column, it is very important to understand. And you have to understand that you have to provide some extra reinforcement, okay, some extra flexure reinforcement to transfer that extra movement. Okay, so what will be the width of in which we have to provide those flexure reinforcement for the amount of unbalanced moment? This is important, which is known as transfer width or effective transfer width. Okay, this is very important. SCA code explain that for an H column, you see here this effective slab width for moment transfer by flexure. Remember, by flexure, it equals to C plus 2 times 1.5 times I pitch this side and 1.5 times I pitch that side, right? This is the width, this dot line you see here, this is the transfer width, and you have to provide extra steel reinforcement right here for the moment, for the extra moment which you got gamma F time MU. Okay, MU, this is the moment MUF. This is the extra moment. Remember, with you have to add this moment. Okay, you have to provide some extra reinforcement for this moment as well. You see, this is the column stress width. In the column stress width, you understand, if you watch lecture number 13, in that lecture we understand as 0.26 m0. Now remember, here is the movement in the column strip, right? This is the movement, okay, which basically exists at the face of the column in the case of the H column, and you have to add this unbalanced movement MUF with, in addition to that movement, okay, which exists in the column strip. But remember, this movement only acting at this transfer width. Remember, this is important. This MUF only acting in this column strip width, not in the total column strip width. Okay, not in the total column strip width. It acts only in this transfer width. and you have to add this with that movement. But remember, that movement should be determined in this width, because that the movement which we got from by using this equation, right, this one. Let's say we find in lecture number 13 I already explained this. Let's say we find the movement from by using this coefficient with them naught. Let's say this is 10 kf. Let's say this is 10 kf feet. Now this 10 kf feet movement is basically acting at the total column strip width, this one. Let's say this is 10 feet. Now you see this 10 kf movement is acting over the 10 feet width, but you see here this transfer width will be smaller than 10 feet. Let's say it is, this width is 5 feet. This transfer width is, let's say this is 5 feet. So what will be the portion of this total movement which exists in this 5 feet? So to find this, you have to just multiply a ratio of 5 divided by 10. Okay, you got the movement which basically act with this in this columns in this transfer width. Now the movement which you got from this, okay, should be add with this one, MUF, right? MUF should be add with this value, and that will be the net moment for which you will design the reinforcement, and that reinforcement would only be provided in this transfer width, remember. And remember, SA code says that you have to properly anchor these bars right at the edge of the corner of this slab and properly in the core of the column, because it transfer movement from the slab to the column. That's why it should be properly anchored with the column. And SA code also recommend that you have to minimize this width, because this transfer width is very important. Okay, you have to properly place these bars, and it is also recommended by the AC code that in the case of a flat slab system, you have to continuously provide 2 bars in the core of the column to transfer the movement from the slab to the column. Okay, so you must provide 2 bars in the column core. This is the minimum criteria, ACI code criteria, right? So there should be proper transfer of movement from the slab to the column. I will explain this in like example, okay? But at this time you must have a concept that what is going on here, okay? And what is transfer width? There is some extra on transfer width. You see in the case of the interior column, let's see, this is C2, so 1 time 1.5 time of H and 1.5 time of H. This is the transfer width. If you are placing, you have to provide the bars within this transfer width, okay, within this transfer width, right? And for how to calculate this reinforcement, it will be calculated by using this equation, okay? So in the case of the exterior column with movement transfer, okay, so you see here this is the transfer width and this is C2 1.5, okay? And similarly this limitation is also important. Sometimes this is the edge of the slab and the column is a little bit cantilever from the edge of the slab, so in that case you see here this is C1, right? And this distance is now CT, right? This is CT. So if CT is less than C1, then according to ACA code you see here that C2 plus this side 1.5H are CT. If CT is less than 1.5 times of H, then use CT, okay? Just add CT. And similarly in this case as well, right? So use minimum column strip width, okay? This is important. Let me discuss it right here. You see sufficient slab reinforcement will need to be provided within a transfer width to carry the fraction of the transfer. I already explained this. Okay, you have to provide sufficient reinforcement within this transfer width, right? You see here, and similar you see here. Okay, and to transfer the moment, the unbalanced moment portion from the slab to the column by direct flexure. The transfer width is defined ACA code. This C2 plus 1.5 times the slab or the drop panel thickness. Remember, if a drop panel is present in the column location, so you have to multiply drop panel thickness. For moment transfer perpendicular to the edge of a slab where no edge beam is present, design recommendation from ACA code required that a narrow transfer width should be used. Narrow transfer width. There's in the case of this C1 and CT case. Okay, this is important. And by just minimizing, you see 1.5, if it is more than CT, so use CT, not 1.5 times of H. Okay, and further indicate the slab bars not anchored in the column will not be very effective for transferring movement to the column. It is also important. Thus, in the year 1962, AC committee recommended that when the movement are transferred perpendicular to the edge of a slab, remember, note down this, if the movement is transferred perpendicular to the edge of the slab, right, in this case, this one, you see this is the edge. If movement is transferred, means movement is acting like in this shape. Now movement is directly transferred perpendicular to the edge of the slab. So in this case, you see, use gamma v is equal to 0.20. This implied that 80% of the movement was transferred by moment reinforcement and 20% of the stresses on the critical shear section located at D by 2. Based on their test on interior slab column joints with square column. Hansen et al. Basically, then they proposed that gamma v will be increased. They increased gamma v to 40% and gamma f increases to 60%. So these are different experimental research works. Okay, and in different cases, as I already explained this, in that if wall present, wall end present, wall side present, so these gamma v and gamma f values will be changed. Remember, this one thing is most important, which I not explain here. You see, the traditional ACA, to understand the behavior of this kind of shear stresses distribution, we have three methods. Remember, one is the beam method, which is a conceptual method, although it's not fully developed method, and the second one is the traditional ACA. We will use this traditional ACA design method, and the one is the you can say for use for the H column, that is the alternate approach by using the Alexander and Simon model. Okay, so we will discuss that inshallah. Here you see, we already discussed it. Okay, but you see what is B1, what is B2, remember, and if movement is about the z-axis, then this notation will be used. And similarly here you see if movement is about the z-axis, then this notation will be used. This is the shear stress distribution due to VU divided by AC. AC is what? AC is the area of the shear parameter, means B0 times the D. B0 into D will give you AC. And this is the shear stress distribution in the case of the interior column, in the case of the edge column. And you see at that side here we have tension, and at that side we have compression. So you see the shear stress distribution, and at that side the shear stress will be calculated by using this equation. And this, remember, this is MUV, mean this is that amount of movement, okay, which is transferred by eccentric shear, means you have to multiply gamma v. This MUV will be what? Okay, you have to know this. MUV is gamma v times what? Times MU, the total unbalanced moment times the gamma v. It will give you MUV, right? And then you have to add these two, you got this result. This will be the net shear stresses. Okay, this is VU2, VU1, or this may be VAB, and this will be VCD. So different book uses different notation. Okay, we will understand this in examples. Similar in the case of the interior column. And okay, you see here, this is now it is denoted by VR, and here it is denoted by VL. So different book, this is the Nelson book notation, okay, and this is the, I think so, this notation is used in the Wang book, right? So we already explained it. Here you see it is CAB distance is denoted by CR, and in the Wang book it is denoted by X2, where it is denoted by CL, but we denote it by CCD or X1. Okay, so different book uses different notation. And this is the McGregor book notation, right? And this is in the case of the interior column, when movement is acting about the x-axis. Remember, this is the interior, so the x-axis, z-axis, okay, they are coincide to each other. And you see this is B2, this is B1, and you see A, B, C, D notations. And in the case of the H column, you see here this is A, B, C, D, and this is B1 if the movement is acting about z-axis. Now you see this is now centroid, and let's say if this is the column, so this is the column centroid. So remember, there will be more shear stresses, as you see here, the more shear stresses, because in the H column the z-axis is close to the face, so that's why there will be maximum shear stresses while there will be minimum, right? But in the case of the corner column, we will see, inshallah, we will discuss it, okay? And in the corner column it will be, we will do the analysis for W axis, we will do the analysis for Z axis, right? We will do examples on it, okay? Now this is important to understand this graph, okay? As we already explained, transfer width, okay? So the bars which is basically provided in the transfer width, okay, those bars must be yield, means there must be tension control section. Now this is the column width. Now if you provide the bars in the column width, they must be yield, and you see here it's yielding you can see epsilon t value, it is more than 0.005 or 0.004. But here you see the bars, if you provide bars right in this place, which is 1.5 times of h, okay, from the outside of the column, so those bar is not reaching to the yielding. You see here these points, these are the bars. So ACA code says that the strain value should be checked right here, and the minimum strain in this region which you are providing outside the column width, that is 1.5 times of h, it must have a strain value equals to 0.010. okay, so we will do check for epsilon t in that region, and we will check that whether epsilon t value is more than 0.01 or not, okay, because the bar must reach to yield point at this location as well. This kind of ACA criteria are very important to understand. It basically says that that you can decrease your VU, allows the designer to increase gamma F from, yes, this is important, that you can increase the portion of gamma F from 0.6 to 1 if the factored shear VU, if the factored shear VU is less than 0.75 times of pi VC. Remember, if you find the value of pi VC and you multiply it with 0.75 and they are still more than VU, you can say that the total movement is transferred by flexure and no movement is transferred by eccentric shear. Okay, so in that case basically your MUV, it becomes 0. Okay, so the calculation will be more simple for us. but if it is greater than, so we will do the whole calculation for the shear stress distribution. Okay. Now, similarly, the same increase of gamma F is permitted at corner connection when VU is less than this value, and okay, and for the interior connection, we have to check this with 0.4 by VC, right? So we will do this check in coming example, right? Now, moment and shear transfer at H column alternate analysis. We will use this equation which is proposed by the Alexander and Sement, and at the last, okay, we will explain this concept. They basically give a short formula for an H beam, how to calculate VU basically. Okay, although we use that lengthy equation, that is P by A and plus minus M into C divided by JC, but they give us a very shortcut equation. By using that empirical equation, you can find this VU very easily, right? The next thing is this one, okay, that you already know this equation. Sometime it may be negative, which is on the back side, and sometime it will be positive, which is on the front side, right? And remember, we have to use only MUV, right? And in the case of the moment MUV together with the vertical reaction, okay, this is the same. And in the next lecture, inshallah, we will stop this lecture right here, and in the next lecture we will explain some properties of the shear parameter. I mean that what is JC, what is CAB, how to determine it, and what for different columns, right? Corner column, interior column, and H column, there have different equations for CAB and CCD and JC. Okay, you will understand this thoroughly, inshallah. So thank you for watching. See you in next lecture.